Okay, well, maybe it's time to start. And it's nice that we have today the meeting of our seminar number 100. And it's a great pleasure for me to introduce our today's speaker, Professor Neena Gupta from Indian Statistical Institute. And the title of Neena's talk is the Abhyankar-Sathaye Epimorphism Conjecture. Please.
Thank you, sir, for the kind introduction. It's my pleasure to give this talk. Today in this talk, I will talk about our recent work with Parnashree Ghosh and Ananya Par. So, yeah, let me begin. So, so we all know about Professor Abhyankar. He always encouraged the study of polynomials and power series and problems related to them. So in a famous paper by survey article by Kraft in 1996, he listed down some problems on polynomial rings, which are easy to state, but some of these problems have turned out to be very difficult. So today I will touch upon the problems, the Zariski's cancellation problem, the affine fibration problem, and the epimorphism problem of Abhyankar and Sathaye. So the main theme involved in some of these problems is to determine whether a given polynomial is a coordinate in a polynomial ring kxn up to xn. So let me fix this notation. Throughout my talk, k will denote any field. K, small k, is always a field. And for any ring R, A equal to R square bracket n means that A is a polynomial ring in n indeterminate over R. So with this notation, the main theme involved in some of these problems is to determine whether a given polynomial f is a coordinate, that is, whether there exist f2, f3, fn polynomials in xn up to xn which generate them, so that there's an automorphism which takes x1 to say f. So this determining or detecting whether something is a coordinate is a very challenging problem. And another challenging problem which come across is, given a ring, is that a polynomial ring? So if suppose you are given a finitely generated K algebra, it is sometimes difficult to determine whether it is itself a polynomial ring. So we first come with the Zariski's cancellation problem. His problem was over field, but this generalized version for rings is also known as a Zariski's cancellation problem. This problem asks whether the affine n space A and K is cancellative as an affine variety. That is, if for any affine variety V, if V cross A1K is isomorphic to the affine n plus 1 space, does that necessarily imply that the affine variety V itself is an affine n space? More generally, for rings, you can ask that whether the polynomial ring kxn up to xn is cancellative. That is, if you have a ring A, and if you consider the polynomial ring in one indeterminate over A, if that is isomorphic to a polynomial ring in n plus 1 variable over the field K, does that necessarily imply that the ring A is isomorphic to a polynomial ring in n variable? This problem was known to have an affirmative answer for n equal to 1, and a more general version was proved by Abhyankar, Ikin, and Heinzer. So, however, the problem for n equal to 2 was not so easy. Miyanishi, Sugi, and with an important contribution from Fujita, the affirmative answer was known for any field of characteristic 0. And later, it was soon generalized by Peter Russell over a field of perfect field. This probably was known that this cancellation is true for n equal to 2 over arbitrary field, but we didn't find any proof, so we gave a proof in 2015 along with Professor Bhartodekar. This solution to the n equal to 2 had led to beautiful topological characterization of the affine plane by C.P. Ramanujan and an algebraic characterization of the affine plane by Miyanishi, which eventually led to the solution of the cancellation problem for n equal to 2, the algebraic characterization. Here we have C.P. Ramanujan. In his short span of life, he has done marvelous work. These are the words of Mumford, that he was a very right kind of attitude towards mathematics. And we have the four giants, Chorus, Russell, Miyanishi, and Gurjar. So they are the people who were involved in this cancellation. Chorus and Russell, they are also well known for their solution to the linearization conjecture for n equal to 3. What I showed was that when K is a field of positive characteristic, then the Zariski's cancellation problem does not have an affirmative answer for n greater than or equal to 3. And this problem is still open over a field of characteristic 0 for n greater than or equal to 3. So this is the status. Now I come back to this example of Asanuma. So Asanuma had constructed this ring in 1987 in his paper on affine fibration. So here K is a field of positive characteristic P, and A is this ring, and this P is this characteristic, and this P, Z to the power P square plus T to the power SP is some polynomial in Z and T, which is a special kind of polynomial, which I will discuss later. So Asanuma had proved that this ring A is an A2 fibration over K small x. So small x is the image of capital X in A. He also showed that the ring A is a stably polynomial ring over K. That is, after adjoining one more variable, it becomes a polynomial ring. And he proved that A is not a polynomial ring over the subring Kx. Later in 1994, in the context of linearization problem, he came across this example again and asked this question: is the ring A necessarily a polynomial ring?
I'm
Note
sorry.
that-
And what is E? There is no E.
Oh, sorry, I changed the slide. So this E was basically P to the power E, but later I made it P square. So this E has not much role here.
Okay, thank you.
Sorry. So this Asanuma had raised this. Yeah.
Also, that equation, what is R?
R is any integer. For Asanuma's ring, R is an integer greater than or equal to 1.
Any integer?
Any integer greater than or equal to 1.
Okay, thank you.
Okay. So Asanuma's question had two consequences. If one can show that this ring A is a polynomial ring, then you have a counterexample to the linearization problem over a field of positive characteristic. On the other hand, if the ring A is not a polynomial ring, then clearly, because of this, A is a stably polynomial ring, we have a counterexample to the ZCP problem for K3 in positive characteristic. Peter Russell called this dichotomy as Asanuma's dilemma. So he is Professor Asanuma. I was very fortunate. He visited ISI when I was a PhD student, and I came across his papers and had discussions with him. What I showed in 2014 was that for this integer R greater than or equal to 2, the ring A is not a polynomial ring. So this problem is still open. Asanuma's question is still open for R equal to 1. And if one can show that for R equal to 1, this turns out to be a polynomial ring, then we have a counterexample to the linearization conjecture as well. Now I come to the affine fibration problem. So for this, let R be any ring, P be a prime ideal of R, and A be an R algebra. Let Kp denotes the field of fractions of the integral domain R mod P, and A tensor Kp denotes the fiber ring of A at P. Then A is called an AN fibration or affine fibration over R if A is flat over R, A is finitely generated over R, and all the fiber rings of A. So A tensor Kp basically are the fiber rings of A at the point P is a polynomial ring in an indeterminate over R. So this is for every prime ideal P of R. This definition of AN fibration is due to Sathaye. In a famous paper, 1994, Dolgachev and Westphaler asked this problem that if R is a regular local ring of dimension D, whether any AN fibration is isomorphic to a polynomial ring. So it's essentially saying that locally this fibration is like a vector bundle or not. So this problem of affine fibration is known to have an affirmative answer for n equal to 1. And when the ring D is the dimension of the regular local ring, for any dimension, the answer is yes. And this was proved by Kambayashi and Miyanishi in 1978. And in fact, my supervisor, Professor Datta, proved it for any, proved that this hypothesis on every prime ideal, you can reduce it to only prime ideals of height at most 1. So this was a deduction of Datta. However, so he's Professor Datta and our Professor Sathaye and I, so they were visiting India, and this is a photo we had together. So however, so now the case for n equal to 2, even for the ring is of dimension 1, the story is very difficult. In a non-trivial paper due to Sathaye, the answer is proved to be yes, and that is when R contains the field of rational numbers. So this is highly non-trivial result. It uses the techniques of expansion techniques, generalization of the expansion techniques, which were developed by Abhyankar and Mo to prove the epimorphism theorem. And later, in 1987, Asanuma constructed an example over a discrete valuation ring that if R does not contain the field of rationals, then any A2 fibration over a is need not be a polynomial ring. So that example which I was discussing is that that was constructed by Asanuma to give this proof that A2 fibration over a DVR need not be a polynomial ring if R does not contain the field of rational numbers. This problem is completely open and very, very difficult if you increase the dimension, even if you consider that R contains the field of rational numbers. However, in positive characteristic, we have generalization to say that if R does not contain the field of rationals, A2 fibrations need not be trivial. So what is the best expected result we can think for any A2 fibration to be? So this is again due to Asanuma. He proved that over a regular local ring, any AN fibration is actually a stably polynomial ring over R. So this is one of the very nice result that that's probably the best we can expect. It's independent of characteristics. So if somebody is looking for counterexamples to the cancellation problem, maybe it will be a good idea to look for counterexamples to the affine fibration problems. Now I come back again to this Asanuma's ring. So Asanuma's ring is of this type. It is a linear polynomial in Y with a polynomial G, which is a polynomial in Z and T. This polynomial G has a special property, that is, it satisfies being a line, that KZT mod G is a line, but G is not a coordinate. A polynomial F is said to be a non-trivial line if capital F defines a line, but it is not a coordinate. Examples of non-trivial lines were given by Segre in 1957 and 58, which was probably overlooked, and later Nagata constructed some family of examples over fields of positive characteristic. What if characteristic of the field is 0? So here comes the very important historical result due to Abhyankar and Mo, which was also proved independently by Suzuki for K equal to C, that there does not exist any non-trivial line over a field of characteristic 0. That is, if kzt mod f is k1, then f must be a coordinate. This theorem we can generalize and ask a question in higher dimension. Suppose f defines an affine n-1 plane. Does that necessarily imply that f is a coordinate? The Abhyankar-Suzuki theorem says that the answer is yes over a field of characteristic 0, and the Segre-Nagata non-trivial lines gives counterexamples over a field of positive characteristics. The Abhyankar-Sathaye conjectures, today's topic of today's topic, asserts that over a field of characteristic 0, this question always have an affirmative answer. And this is completely unknown is not known for more general situations for n greater than equal to 3. Some partial results are known for n equal to 3 and onwards. So far, do you have any questions? So then I can proceed. Any questions so far? No. Okay, so let me move ahead. So the conjecture is that over a field of characteristic 0, if f defines an affine n-1 plane, does that necessarily imply that f is a coordinate? Sathaye had proved over a field of characteristic 0, and later soon Russell in an independent paper, he proved it for any field, that if G is a linear plane, that is, if G is of special type, that it is linear in Y, then the answer is yes. In fact, they proved much more general thing. They proved that you can find a coordinate x1 in x and z such that the leading coefficient of y is actually a polynomial in x1 and G is a coordinate along with x1. So in view of this Sathaye-Russell theorem, one can ask this question in higher dimension and consider any polynomial G of this type, that is axy minus bxzt, and ask the question, is G necessarily a coordinate along with x if G is an affine 3 space? G defines an affine 3 space. Does that necessarily imply that G is a coordinate along with x? In 2014, I showed it for when ax is of special type x to the power r, where r is greater than 1. There are there are other results on epimorphism problems. The first one is due to David Wright and Prosenjit Das and Data. So David Wright had proved when K is an algebraically closed field of characteristic P greater than equal to 0, and F is of this type, that is A and B are polynomial in X and Y, but with Z to the power n is an integer greater than 2, strictly greater than 2, and P is not dividing n equal to 1 case is the Russell-Sathaye case. So n not greater than equal to 2. If F defines a affine plane, then F is a coordinate. Later, Das and Datta, they generalized this result for any field of any field, need not be algebraically closed. However, this condition P not dividing n is necessary, otherwise we have counterexamples. In fact, the Segre-Nagata line itself will give you the counterexamples. Sathaye and Russell, in their non-trivial paper, they proved that when K is a field of characteristic 0 and F is of this type, with this F you write it as a general polynomial in Z with one hypothesis, that this coefficients of Z, the ideal generated by that, is non-trivial. Basically, the GCD of A1, A2, AN is not 1, is not an unit. Then if F defines a coordinate, F defines a affine 2 space, then F must be a coordinate. Kaliman, he proved that if G is a sufficiently general plane, that if almost all the fibers of G defines an affine 2 space over the field of complex numbers, then G must be a coordinate. I understand that this result has been proved for a field of characteristic 0 also, any field of characteristic 0, that if almost all the fibers of G are C2, K2, then G must be a coordinate. There are other results on epimorphism problem due to Kaliman, Venera, Zedenberg, but because of lack of time, I have not included those in my slides. Now I come back to our results. So this asynchronous example was of this type, x to the power ry, and this z to the power p square plus t to the power sp. When I solved this example for r greater than 2, Peter Russell posed me this problem that where is it you have used f as a non-trivial line? So his question was that suppose f is any non-trivial line, is this ring A necessarily not a polynomial ring? There was another famous example, which is known as a Chorus-Russell threefold, which is at the moment a very suitable candidate. No, it's a potential candidate for counterexample to the cancellation problem in characteristic 0. That this ring, this Chorus-Russell threefold, at time it was not known whether this is a polynomial ring, and Makalimanov proved that yes, this is not a polynomial ring. So this ring and asynchronous ring are of some similar nature because both of them are linear in Y, with the difference that this is strictly for field of positive characteristic and this is complex number. So this led me to consider this more general ring where K is a field of any characteristic and F is any polynomial in 3 variable. And we obtained this result that if B is a polynomial ring in 4 variables and G is this coordinate, G is of this type, and small f is the F capital F0 ZT, then we proved the equivalence of the following statements. That is, this ring A is a polynomial ring if and only if it is a polynomial ring over the subring Kx, where X is the image of the capital X in A. Moreover, if these conditions are satisfied, then small f is necessarily a coordinate in ZT. And this is equivalent to say that capital G is a coordinate in B and B is a polynomial ring over X and G. So we see that this theorem includes the asynchronous threefold as well as the Chorus-Russell threefold, with one condition that this integer r must be greater than 1. This investigations for this threefold had led me to consider this more general ring in higher dimension. Again, I have made it linear in Y with the coefficients. It's a product of x1 to the power r1, xm to the power rm. These are the product of this first m coordinate, and each integers ri's are greater than 1. Then we proved that this investigated these problems. When is this ring A is a polynomial ring? When is this A stably polynomial ring? That is after adjoining one more variable, it becomes a polynomial ring. And when is this polynomial in the denominator is a coordinate in kx up to xm, yzt. With Parnashree, I obtained these results, Parnashree Ghosh, that if I consider this ring A, where capital F is of a special type, so I need to take capital F is a polynomial in Z and T plus x1, x2, xm times G. So this is a sort of special type. Otherwise, if I don't take this assumption, then we don't have the equivalence. So we proved similar statements in the higher dimension, the ones which we have got for M4. So we proved that this ring A is a polynomial ring if and only if small f is a coordinate. So thus the problem in m plus 3 variables have been reduced to a problem in just 2 variables, and it's easier to determine whether a polynomial in 2 variable is a coordinate or not. And if this is the case, then G is a coordinate, and actually G is a coordinate along with x1 up to xn. And in that case, A becomes a polynomial ring over the subring kx1 up to xn, where small xi denotes the image of capital Xi in A. So these are the consequences we obtained. So for any field, and Ris are positive, strictly greater than 1, and if G is this polynomial, capital G, then the statement that A is a polynomial ring in m plus 2 variable, if and only if small f is a coordinate, is a very strong kind of statement, because this involves m plus 3 variables, and this is just 2 coordinates. So it provides a general framework for understanding the non-triviality of the Korus-Russell threefold. So in this Russell-Korus threefold, small f is z square plus t cube, which is clearly not a coordinate. Therefore, we have this result. Further, this ring A is isomorphic to a polynomial ring in m plus 2 variable if and only if G is a coordinate along with xn up to xn. So this, in some sense, generalizes the Sathaye-Russell theorem for linear planes for the case n greater than 3. And it is also an example where the Abhyankar-Sathaye conjecture is true. So A is a polynomial ring, implies G is a coordinate. And the fact that A is a polynomial ring forces that A must be a polynomial ring over the subring kxn up to xn. Therefore, and this condition will be satisfied if and only if small f is a coordinate. Therefore, if you want to construct a non-trivial A2 fibration, then small f must be a non-trivial line. And this is in some sense gives you a way to get more examples of non-trivial A2 fibrations. We also proved that if K is a field of any characteristic, and I consider this ring, then when capital F is of this type, small f plus x1 up to xm G, then this, and f is a line, that is kzt mod f is k1, then A is a stably polynomial ring. That is, after adjoining one more variable, this ring A becomes a polynomial ring. Now, recall that by the previous result, if small f is not a coordinate, then this ring A cannot be a polynomial ring. But if f is a line, then it is a stably polynomial ring. So this is where it gives you a recipe for constructing counterexamples to the Zariski cancellation problem, because here we actually not using anything which is characteristic dependent. What I am using is that if there is a line, then it becomes a stably polynomial ring. And if f is not a coordinate, then A cannot be a polynomial ring. So whenever you can give me an example of a non-trivial line, you have a counterexample to the ZCP. And we now know from the Abhyankar-Suzuki's theorem that non-trivial lines exist only in positive characteristics. Further, we also proved that if this ring A, there are some parameters R1, R2, Rm, these are the positive integers, and small f. So these are the parameters which defines the ring A. We proved that two such rings are isomorphic if and only if this R1, R2, Rm is equal to S1 up to Sn up to some permutation, and F and G are equivalent. Equivalent means they define the same ideal in the ring KZT. So in some sense, we can vary these integers R1, R2, Rm, and we know that all such rings, after adjoining one more variable, they become a polynomial ring. Thus, over a field of positive characteristic, we have an infinite family of non-isomorphic rings, which are all stably isomorphic to the polynomial ring in m plus 2 variables. This again we obtained in a joint work with Parnashree Ghosh. Now, what's the ingredient, means what is the tool which I am using? So the tool which I am using is an application of exponential maps. Exponential maps are same as the GA actions, the action of the additive group K plus on an affine variety. So which we can define algebraically as a ring homomorphism from a ring A to a polynomial ring AU, and satisfying the following two properties. So these two properties corresponds to the two axioms of the group actions. So that is, this composite map phi underscore u denotes the phi underscore u denotes the coordinate u which we are using. So this says that this composite and epsilon naught is the evaluation map, putting u equal to 0. This composite is identity, and phi v composed phi u is phi v plus u. So where phi v is the exponential map phi, and which we can extend to AU by sending u to just u as an identity. So this is phi v composed phi u is phi v plus u. So these two are the two axioms of the group actions K plus. So for an exponential map phi, we can define a collection of all those elements in the ring A which are fixed by phi. This will turn out to be a ring, and this is known as the ring of invariant, phi invariants. For example, the simplest known exponential map is for the polynomial ring Kx is sending x to x plus u. So here phi is an exponential map. One can easily see that. And the ring of invariant, which is fixed, is K. An exponential map phi, I said to be non-trivial if the ring of invariant is a proper subring of A. The Duksan invariant of a ring A is a subring of A generated by A phi, where phi varies over all non-trivial exponential maps on A. And it is denoted by dk of A. For example, the decay invariant of the polynomial ring is the whole ring whenever n is greater than 1. So if A is a polynomial ring kxn up to xn, we can consider the exponential maps phi I, which defines xj to xj plus delta ij u, where delta ij is the Kronecker delta symbol. That is, it moves only xi. Phi I moves only xi and fixes other xj. So here the ring of invariant is kx1, x2, xi minus 1, xi plus 1, and xn. Now clearly, if we have two different I not equal to j, then this together phi a phi I union a phi j will give me the whole ring here. Another invariant which Makalimonov discovered, known as Makaliman invariant of the ring A, is a subring of A obtained by the intersection of A phi, where phi varies over each non-trivial exponential map on A. And it is denoted by Makaliman invariant of A. For example, the Makaliman invariant of the polynomial ring is K for n greater than 1. So the phi I, the exponential map which we just now considered, if we consider this phi I, then a intersection of all phi 1, phi 2, phi n will give us K. Now, this is the theorem which we proved with Parnashree. So here G is this polynomial and capital F is of the special type. We give an equivalence of 14 statements, which each statements of a different flavor, which has connected problems like cancellation, epimorphisms, and vibration problem. So the first 5 equivalent conditions we have already seen. The next 4 conditions are basically when we assume that the Duksan invariant of the ring A is whole ring. So note that this is my ring A. And if A happens to be a polynomial ring, then Duksan invariant is necessarily the whole ring. So we showed that if I assume that the Duksan invariant is the whole ring, then it's enough to assume that A is a stably polynomial ring, or if A is an A2 fibration, or if small f is a line. And this is probably the minimal condition that the ring A is a UFD with a trivial Dakshan invariant, and the units of this ring A mod xia is coming from K. So similar such statements we also have obtained for Makaluman invariants. So whenever the Makaluman invariant of A is trivial, that it is K, then we have some similar conditions. There was one more condition which I have not listed down here. So this is so far with Parnashree. Recently with Ananya Pal and Parnashree Ghosh, we obtained this result where K is a field of characteristic 0 and G is a polynomial in linear polynomial in Y, but with AX is any coefficient of Y and A is this ring. Then we proved the equivalence of the following statements. In fact, we have equivalence of two more statements which I have not written down here. So the fact that this ring A is a polynomial ring is equivalent to the fact that this ring A is an A2 fibration of the subring Kx, or is a polynomial ring over the subring Kx. And this three, or any of them, it implies that the ring B is a polynomial ring over Kg. That is, G is a coordinate. So we have proved that this Abhyankar-Sathaye conjecture for the AXY plus fxzt is true for field of characteristic 0. And in fact, it's a generalization of Russell-Sathaye's theorem of linear planes in 4 variables, where you can take prove that G is a coordinate along with X. And these 5 statements are equivalent to the fact that whenever, for every root lambda of AX, if I look at the extension field K lambda, and K lambda Z is K lambda F lambda ZT1 for every root lambda. So it may happen that AX does not factorize, or it is irreducible in Kx, but it factorizes above. But then at above, these conditions are being satisfied. So this is for field of characteristic 0. We also have examples over a field of arbitrary characteristic here, but we have to assume some more conditions that this AX has only multiple roots. So if AX has simple roots, we don't know what will be the answer. But whenever AX has only multiple root, we obtained that this ring A is a polynomial ring if and only if it is a polynomial ring over the subring Kx. And then it will follow that B is a polynomial ring over the subring Kg. And in fact, B is a polynomial ring along with X and G. And these 4 statements are equivalent to the fact that for every root lambda of AX, F lambda ZT is a coordinate in K lambda ZT. Another special case we obtained over a field of any characteristic is that with this assumption on AX is that here capital F is equal to small f. That is, it does not involve any X here. There is no X here. But with an assumption that AX has at least one multiple separable root in K bar. So it has a multiple root, which is a separable root. And then we proved the equivalence of these 5 statements. So which is similar to the previous one, that this G is a coordinate along with X. And if and only if this small f is a coordinate. We don't know how to tackle this problem in characteristic, arbitrary characteristic, but somehow I believe that it must be true for a field of arbitrary characteristic. We at the moment we are working on some other projects in higher dimensions, but they're very rough kind of statements, which is probably difficult to prove. We state right now, so I'm not getting into that. I will just end the talk with an example due to Bhatwadekar and Datta. So this example here, A is a polynomial ring in 4 variable, and R is a subring of A generated by T and F, where F is a linear polynomial in Z. So note that Z is degree 1 with the coefficient T times x square and x plus t square y plus tx y square. This is a modification of their example, which Professor Datta had written down in his thesis. So he proved that this ring A is an A2 fibration over R. Moreover, A is a stably polynomial ring over R. And F defines an affine 3 space. That is, A mod F is actually a polynomial ring over CT. So it's a generalization of quotients by linear plane due to Russell and Sathaye in 4 variable. And the question which remains open is that whether A is a polynomial ring over R. That is, and this is probably, I don't know, this may have positive solution or negative solution, but at least whether one can say that A is a polynomial ring over the subring CF. And if by some misfortune this answer is no, then all these 3 problems will have counterexamples. The A2 fibration problem over C2, cancellation problem over C1, and the Abhyankar-Sathaye epimorphism problem for the projection C4 to C3. So here's a picture of Professor Bhatwadekar, Professor Avinash-Sathaye, and Professor Datta. I end my talk with paying tribute to these 3 peoples and Professor Asanuma, who played a very pivotal role in shaping my research work. Thanks.
Thank you very much for your talk. So, dear colleagues, any questions, comments?
Let me ask you, first of all, it's nice to see you for the first time.
Also happy to see you.
There is this generalization of epimorphism question. You have an embedded affine space in an affine, properly embedded in an affine space of higher dimension, not necessarily hypersurface. And the question is whether you can rectify it. So do you have potential counterexamples to this question? Did you give a thought to this problem?
Yeah, so this Bhatwadekar Datta's example is a potential counterexample for the rectifiability. So this example, so when you go modulo F, it is C3.
Right.
And one doesn't know whether F is a coordinate, which is same as rectifiability.
Yes, I understand, but say if you have C2 properly embedded in C4, I'm not speaking.
C2 and C4, C2 and C4 is probably not known.
Yeah, it's not known, but maybe
Yes.
you have something in mind as a counterexample.
I don't have any candidate of C2 and C4.
Okay.
Yeah, C2 and C4 is probably not known. C1 and C4 is done. Yeah, that is easy. Maybe not easy. Once the problem is done, it is easy. So once the solution is known, it is easy. But till the time it is not solved, it's difficult. So
maybe you can mention about C1 to C3.
Yes. Yes.
C1 to C3 is again open.
Right.
No, there is a candidate, right? The Shastri's example.
Oh, yes. Yes,
No.
yes.
No, I don't know. I don't know if Shastri's example provide a counterexample in the case of.
No, so that's an open problem.
So
That is
Shastri
open.
concrete candidate.
it's a candidate, but over complex numbers, it's not a counterexample.
No, no, no. It's still open.
It's still open.
Yes. One doesn't know how to tackle that. Maybe there is some machinery, one has to actually work it out. Probably it's a different algebraic way of thinking may help. I don't know. Or maybe topological things will not help, far as I understand that topologically there is no obstruction for ring rectifiability. This is I know very little of topology and geometry, so I handle things using just Macaulay-Monod induction invariants. So I also don't understand them very well. So what I know from reading papers is that topologically there is no obstruction for the Shastri's example.
No obstruction over C.
Over C, yes.
Over R, it is a counter example, right?
Yes, yes. And over R also we don't know exactly. Yeah, over R it is a counter example, yes.
For topological arguments.
Right. It's a non-trivial knot, so indeed you cannot, over you cannot rectify it.
In fact, I came to I don't know whether it is true or not, that this Shastri's example, it is this kernel is known to be 2 generated, but one doesn't know the actual generators. So I have computed the actual generators long time back, but I don't know how to use it. So maybe.
Okay, thank you very much. So please, any more questions, suggestions?
I have a question. In theorem 1, you can require the degree is one, but before that theory, you always ask that R is bigger than 1.
Yes.
Does this require is very important?
Yes. So for this asynchronous ring, let me just say, before
Yeah.
all these things is for any integer R.
Yeah.
But
Yeah.
my results, moment it comes to my results, I assumed that R is greater than equal to 2. Because for R greater than equal to 2, I could prove that the Duksan invariant or the Macaulay-Monod invariant of these rings are non-trivial. So if for R greater than equal to 2, the Macaulay-Monod invariant is Kx.
If
You
for
put
the
R equal to
for
1,
that,
then the Macaulay-Monod invariant becomes the whole ring.
okay. If for letter you always Ri or R1 to Rm. In that
Yeah,
case,
so later on we always assume Ri's are greater than 1.
for letter
Yeah, this slides onwards. Ri's are always greater than 1. Similar is
this one. That is to say, if you require one of the Ri is 1, you can also have the result that isomorphism.
the stable isomorphism does not require Ri to be greater than 1.
Okay.
But for the equivalence of these statements, Ri's are strictly greater than 1. So the asynchronous type of results you can still have for Ri equal to 1. But moment you want to prove it is a polynomial ring, then I assume Ri is greater than 1. Because if some Ri is equal to 1, then the Macaulay-Monod induction invariant becomes the whole ring. So that will create a problem.
Okay. Okay, thank you.
Thank you.
Okay, so please.
Macaulay-Monod invariant will be K, right? And
Yes,
Duksan will be whole ring.
the whole ring. Is Parnashree, say we worked it out together.
Any more questions?
There are also potential counterexamples due to asanoma, right? Regard-
Yes, so that counter examples will be for C2 to C5. No, let me think. No. So there are two variables and 6. So yes, C2 to C5. 6/2. So it is C2 to C6. The embedding problem of rectifiability, the potential counterexample due to asanoma, but they are not epimorphism problem. I think it is not known whether there's a polynomial ring, right? That's an open problem.
Yeah, it's open.
Their stably polynomial ring is known, but whether they're polynomial ring, that is not known.
Dear colleagues, so please, any more questions? If not, then let us thank Neena Gupta for this excellent talk. Thank you very much.
Well, thanks for the invite and very glad to meet you all together again.
Okay, so our today's session is closed and we will start our next 100 section of our seminar. Thank you very much.
Congratulate you all for participating in continuing it for till the 100th. And I'm sure there will be many more hundreds to come in this series.
Okay, thank you for being with us. So see you.